Welcome to the deep dive. Today, we are zooming in on a field that sits right at this fascinating intersection. Chemistry, quantum physics, and, well, radical engineering. Molecular magnets.
Yeah, we're talking about structures, so incredibly small individual molecules, sometimes just short chains, that behave like, miniature classical magnets.
But they also have these strange, almost spooky quantum mechanical properties hidden inside. It's definitely a complex field, but really rewarding.
Absolutely. And we're going to try and unpack the three major revolutions it seems to promise, everything from quantum computation to advanced refrigeration.
Right.
Our mission today really is to cut through some of the heavy physics and distill the key insights. We've looked at sources spanning, decades of research into quantum tunneling, these extreme magnetic dynamics, and all the next-gen applications.
As we're tracking the physics, the history.
And most importantly, those three big application areas you mentioned, quantum computation, spintronics, and magnetic refrigeration. That's the goal. And
I think the initial nugget, the thing you really need to grasp up front, is just the scale of control we're aiming for here. We're not talking about, big alloys or bulk materials. We're talking about chemical synthesis giving us this incredibly precise magnetic isolation.
Exactly. And our sources confirm that these single molecule magnets, or SMMs as they're called, they're seriously considered potential two-level qubits.
Which are the basic memory units for, the future of quantum computation.
Yeah, that shows you just how fundamentally game-changing these systems could be. It's really profound stuff.
Okay, so let's unpack this core idea then. SMMs. What makes them so special compared to, a tiny shard of iron or something?
Well, they're fascinating hybrids, really. They manage to marry classical macro-scale magnetic properties, specifically, holding on to magnetization without an external field.
Like a tiny permanent magnet?
Exactly. But they combine that with nanoscale quantum effects, all within a single chemically defined molecule. So think of it like a permanent magnet that is simultaneously a single quantum mechanical object. It's pretty wild.
Okay. So if you take a conventional magnetic nanoparticle, just a tiny piece of magnetic material, and you cool it right down, what happens then?
With a conventional nanoparticle, if you drop the temperature low enough, the thermal energy just dies down, the fluctuations stop,
right,
and the magnetic moment eventually just freezes into a fixed direction. The material becomes magnetically ordered. Below a certain temperature, its ability to just spontaneously switch orientation, it vanishes.
But SMMs, they don't do that.
No, they don't. They show this thing called superparamagnetism. That's the ability to switch their magnetization direction spontaneously, and this keeps going right down to temperatures near absolute zero.
Wow. So why, if there's no thermal energy?
Because the reversal isn't driven by heat anymore. It's driven by quantum transitions. The molecule itself might be physically frozen in the crystal lattice, but the magnetic direction, the spin orientation, it can still tunnel, flip right across the energy barrier.
Quantum tunneling.
Okay.
And the molecule that really sort of put this whole field on the map, we have to talk about Mn₁₂-acetate, right? Mn₁₂.
Oh, absolutely. It's the cornerstone. The molecule itself, its full name is Mn₁₂-O12-CH3CuO16H2O4. It was actually first synthesized way back in the 1980s by Lys, a German chemist.
Really? That early?
Yeah. And for years, it was just seen as another, unusual cluster molecule. Its magnetic secrets weren't really appreciated until the 1990s.
So what is it about its internal structure? It's quite complex, isn't it? How does that complexity make it act like one big magnet?
It's a beautifully complex cluster, yeah. It has this huge collective spin, S equals 10, which is massive for a molecule.
Yeah.
And this large spin isn't just 12 individual moments acting alone. It's a cooperative thing, arising from a core shell structure. You've got an inner shell of 4 manganese 4+ ions, each with spin 3/2,
Okay.
and an outer shell of 8 manganese 3+ ions, each spin 2. And crucially, all these spins are strongly coupled anti-ferromagnetically.
Meaning they align pointing in opposite directions.
Exactly. But the cancellation isn't perfect. It's like they fight each other, but there's a leftover imbalance, leaving this massive net collective spin of S equals 10.
Right. And that strong, complex internal arrangement, that gives it a significant magnetic anisotropy barrier, which is basically the energy hill the spin needs to climb to flip over.
Correct. That barrier is key. Classically, it's measured at around 60 Kelvin. That's a very, very high energy barrier for just a single molecule. It's what gives it that permanent magnet-like property at low temperatures.
Okay.
But the real revelation, the aha moment, came when researchers started looking really closely at its behavior below about 4 Kelvin.
So hang on. If the molecule is physically frozen below 4K, And the classical energy barrier is way up at 60 K. Nothing should happen, classically speaking. It should be stuck.
Classically, yes. It should be completely stuck.
It's flips. So what was the specific experimental breakthrough? How did they finally see this quantum tunneling signature back in '96?
The crucial observation, the smoking gun, was the stepwise hysteresis loop. This was the definitive experimental proof of quantum tunneling of magnetization, or QTM.
Hysteresis loop.
Yeah.
That's when you plot magnetization against the applied magnetic field.
Exactly. And for a classical magnet, you'd expect a smooth curve as you sweep the field back and forth.
But here, instead of smooth, you see steps, like a staircase pattern on the graph. Why does that happen?
That staircase shape tells you something profound. It shows the change in the spin projection, the says value, doesn't happen continuously or gradually. It happens suddenly, in jumps, and only via QTM between specific resonant magnetic energy levels.
Okay, can we try and visualize that energy landscape?
Yeah.
Help us picture what's going on.
Sure. Imagine the energy of the different spin states. You can picture it as a symmetric double well potential. It looks kind of like a W.
Oh, W, okay.
The two bottom points of the W, the wells, represent the spin pointing fully up, say positive says, and the spin pointing fully down, negative says. And they're separated by that anisotropy barrier, the hump in the middle of the W.
And if there's no magnetic field applied?
If the magnetic field is 0, then the opposite states, like M equals +10 and M equals -10 for Mn₁₂-acetate, they're perfectly level. They have the same energy. They're degenerate.
Okay, then you switch on an external magnetic field, H.
Right. And when you apply the field, it's like tilting the entire WS potential. One well goes down in energy, becoming the stable ground state, and the other well, the one pointing against the field, goes up. It becomes metastable, higher energy.
So normally the spin would need enough thermal energy to kind of climb over that central peak to get to the lower well.
That's the classical picture, yeah. Thermal activation over the barrier.
But the magnetic field does something else too, doesn't it? It acts like a tuning knob for the quantum mechanics.
Precisely. It's a tuner. The field doesn't just tilt the whole potential, it also shifts the individual energy levels within each well. These levels correspond to the different spin projections. Okay.
Oh.
And here's the key. When the external field reaches certain specific discrete values, let's call them HM, the energy level of a state in the higher metastable well, say state lines up perfectly. It resonates with the energy level of a state on the other side, the stable side, say state 1.
They become equal in energy,
Right.
even though they're on opposite sides of the barrier.
Exactly. And when these resonant levels coincide, bam, a tunneling channel opens up instantaneously. The spin doesn't need to climb the barrier. It can quantum mechanically tunnel straight through it.
And that causes the sudden jump in the overall magnetization that we see as a step on the graph.
That's the step. The field is literally opening these quantum doors, but only at specific quantized field values.
And for Mn₁₂-Ac, these steps, these field values, they're predictable.
Absolutely predictable, based purely on the molecule's intrinsic spin properties and the anisotropy. The separation field, V0, between these steps is consistently measured at about 0.45 Tesla for Mn₁₂-Ac.
Wow.
This perfect quantization, this staircase pattern, is the definitive proof that the physics governing the spin reversal at these ultra-low temperatures isn't classical thermal hopping, it's purely quantum mechanical tunneling.
Okay, that explanation of QTM, it sets the stage beautifully, but it sounds like a relatively slow, measured, single-molecule process. Now we need to shift gears to something much more dramatic, almost violent. These sudden collective reversals known as magnetic avalanches or sometimes macroscopic Barkhausen jumps. How does that gentle quantum flip scale up into this, well, catastrophic event across the whole crystal?
Right, it's a huge jump in scale. These avalanches are a really profound example of how a single microscopic quantum event, one molecule tunneling, can trigger a macroscopic collective reversal of magnetization across an entire crystal sample. We're talking potentially millions, even billions of molecules flipping almost simultaneously.
Sounds explosive. And this leads us straight into this concept with a frankly terrifying name, thermal deflagration.
Yeah, deflagration is the term used for this runaway process, and it does begin with that initial quantum tunneling event we just discussed.
The first domino.
Exactly. One spin tunnels from its metastable state, the higher energy side of the W potential perhaps, to an excited state on the stable lower energy side. Now that transition releases energy. Specifically, it releases Zeeman energy.
Which is the energy stored by the spin due to the external magnetic field.
Correct. And the amount is significant. Delta E equals 2 times G times MUB times H times S.
And for Mn₁₂-AC, G is about 2, S is 10. So even for one molecule, if H is reasonably large, that's quite a packet of energy being released, isn't it?
It is. And this energy gets dumped directly into the crystal lattice as heat, as phonons. Now remember, we're often doing these experiments at cryogenic temperatures, maybe below 1 Kelvin.
Where the heat capacity of the material is tiny.
Exactly. The lattice can barely absorb any heat without its temperature shooting up locally. So even the energy released by a single molecule tunneling causes a substantial local temperature spike right around it.
Ah, and that spike then affects its neighbors.
Precisely. This released heat drastically accelerates the thermal magnetic relaxation rate in the neighboring SMM molecules. They're now hotter, so they're much more likely to flip thermally over the barrier or maybe tunnel faster from excited states.
And when they flip, they release their own Zeeman energy.
Which heats up the next layer of neighbors, making them flip faster, releasing more heat. It's an exothermic chain reaction, a thermal runaway that propagates through the crystal, much like a flame front spreading through a flammable material.
It's literal ignition.
It really is. And experimental evidence confirms this vividly. Direct temperature measurements on the crystal during an avalanche show an abrupt, massive spike in temperature, signaling this thermal ignition front sweeping through the sample. It can heat up by several Kelvin almost instantaneously.
Okay, that's a fascinating link between quantum trigger and classical thermodynamics. But then the sources push it even further, proposing something maybe even more exotic. Cold deflagration. This is supposed to happen hypothetically right at absolute zero, T equals 0 K, where there's no thermal energy at all. How can you get a collective flick without heat driving it?
Right, this is where things get really interesting and rely on subtler interactions. Cold deflagration is, as you say, more of a theoretical proposal, and it hinges on the influence of the weak, long-range dipolar fields between the molecules.
Dipolar fields. Those are just the magnetic fields produced by each molecule acting like a tiny bar magnet affecting its neighbors.
Yes. In Mn₁₂-ec crystals, the molecules are about 1.5 nanometers apart. That's too far for the strong short-range exchange interactions to play a role.
Okay.
But the longer-range dipolar interactions, they're still present. They're weak, maybe only around 40 to 100 millitesla, much weaker than the anisotropy barrier, but they connect every molecule to every other molecule.
But if they're so weak, how can they possibly cause a collective avalanche at zero temperature? They can't provide energy like heat does.
They don't provide energy in the same way. They don't help molecules hop over the barrier. Instead, they mediate a kind of self-consistent collective resonance.
What does that mean?
Imagine the system starts to relax just a tiny bit. Maybe a small cluster of molecules tunnels first. This flip instantly changes the local magnetic environment, the net dipolar field felt by all the other molecules nearby.
Ah, so the internal field changes.
Yes. And in the cold deflagration model, this change in the internal dipolar field propagates and creates an inhomogeneous state across the crystal. The system effectively self-adjusts the total magnetic field, external plus internal dipolar, experienced by different molecules.
To what end?
To bring a macroscopic number of spins, potentially millions of them, to the precise resonant tunneling condition all at the same time.
So instead of just relying on the external field H to hit those magic resonance values, the molecules themselves, through their collective dipolar interactions, create fine-tuned local fields that push huge numbers of them onto resonance simultaneously, allowing a massive collective quantum tunneling event.
That's the core idea. It bypasses the need for thermal energy entirely, relying only on this cooperative adjustment mediated by the weak, long-range magnetic coupling. It's an amazing example of potential self-organization in a quantum system, leading to a massive collective quantum leap.
Okay, that's pretty mind-bending. And given the huge number of molecules flipping together coherently in this picture, the sources mentioned another possibility. Something about intense energy emission.
Yes, and this is perhaps one of the most tantalizing and still debated aspects related to these avalanches. The potential connection to Dix superradiance.
Superradiance, like lasers.
Sort of, but with spins instead of electron transitions. The idea is if this cold deflagration process, this self-organization, results in a highly ordered state where a macroscopic number of molecules are effectively phase coherent and tunnel together.
A synchronized quantum jump.
Exactly. This collective coherent decay of the spins from the metastable state could, in principle, emit an intense, highly directional burst of electromagnetic radiation. Because it's a magnetic transition, it would likely be in the terahertz frequency range.
Wow. So a kind of microscopic, organized magnetic detonation inside the crystal that releases a powerful pulse of terahertz light. It's quite a prospect.
It is. It remains an unresolved mystery whether this truly happens, but it highlights how these systems bridge fundamental quantum mechanics like QTM with potentially massive collective energy release phenomena. It offers this unique window into studying non-equilibrium dynamics in strongly interacting quantum systems.
Okay, let's shift from those high-energy dynamics now towards information science. We're seeing this convergence, right? Molecular electronics, spintronics, and quantum computing all coming together. This idea of molecular quantum spintronics.
That's right.
And the big advantage molecules seem to offer here is using the specific chemical environment within the molecule, especially in organic structures. Things like weak spin-orbit coupling and weak hyperfine interactions, using that environment to actually shield and preserve the quantum information stored in the spin, preserve its coherence.
Spin coherence is absolutely the name of the game for any quantum computing application. It's the single most critical metric. If we want to use SMMs or any spin system as a useful qubit, it has to be able to maintain its delicate quantum superposition state long enough for us to perform calculations.
And we measure this coherence using two main timescales.
Yeah, the two key times are tone and 2-2. Tone is the longitudinal or energy relaxation time, basically, how long the qubit stays in its excited energy state before decaying back down. 2 is the transverse or phase coherence time. That's how long the qubit maintains its specific quantum phase relationship, the superposition itself.
And you mentioned earlier, for molecular magnets, especially at low temperatures, T2 is often the big problem. It's much, much shorter than tone. Why do we lose that phase information so much faster than the energy?
It's a great question. Tone decay usually involves coupling to the environment in a way that exchanges energy, like emitting a lattice vibration, a phonon. At very low temperatures, there aren't many phonons around, so tone can actually be quite long, seconds, or even longer sometimes.
Okay.
2 decay, the dephasing, is much more fragile. It's incredibly sensitive to any kind of magnetic field inhomogeneity or fluctuations in the local environment. Even tiny variations in the magnetic field across the sample cause different spins to precess at slightly different rates.
Like runners getting out of sync.
Exactly like that. They start together, but tiny differences make them drift apart. And eventually, the overall phase relationship, the coherence, is just washed out. And for SMMs in bulk crystals, the primary culprit causing these field variations are those very dipolar fields we just talked about.
Ah, the 40 to 100 millitesla from the neighbors. Even though they're weak, they're not perfectly uniform, are they?
Not at all. Every molecule sees a slightly different dipolar field from its neighbors depending on their exact arrangement and spin state, and that tiny difference is enough to kill the phase coherence, the T2, very quickly, often in nanoseconds or less in concentrated crystals.
So how close are we then to actually proving that these molecules can even operate coherently as qubits? Can we manipulate them quantum mechanically?
Oh, we're definitely past proving they can. We have direct experimental observation of coherent quantum spin dynamics, even at the mesoscopic scale involving many spins. The key evidence comes from measuring Rabi oscillations.
Rabi oscillations. That's when you hit the spin with resonant microwaves, and it flips back and forth between its states.
Precisely. You drive the transition coherently. Seeing those oscillations is proof that you're manipulating a quantum superposition state. For instance, studies on systems like erbium ions diluted in calcium tungstate ER3+ in CaRe-WO4 showed clear Rabi oscillations with a characteristic damping time, sort of a measure of coherence during manipulation of about 0.2 microseconds.
Okay, 0.2 microseconds, that's measurable coherence.
Yes. It confirms we can initialize, manipulate, and observe a coherent quantum state in these types of molecular spin systems. It paves the way for what people are calling electronuclear mesoscopic spin qubits.
0.2 microseconds, while proof of concept, is still incredibly short for doing any serious computation, right? If those dipolar fields in bulk crystals are the main bottleneck killing T2, how do we get around that? How do we push 2 into a useful regime, like milliseconds, maybe.
Yeah, microseconds is still way too short for fault-tolerant QC, so the
Okay.
standard first approach to fight dipolar broadening is pretty straightforward,
Doing it.
physical dilution.
Just spread the molecules out.
Exactly. You take your SMMs and you dissolve them, then freeze them in a large matrix of an inert, non-magnetic solvent or host material. You physically separate the magnetic molecules from each other, sometimes by tens of nanometers.
Inducing those neighbor dipolar interactions.
Right, and this does work. Dilution studies have successfully pushed 2 times up significantly into the range of a few microseconds for some SMM systems.
Okay, better, but still maybe not long enough. And also, freezing things in a dilute solution doesn't exactly sound like the basis for building a scalable quantum chip, does it?
No, it's not very practical for device integration. It's great for fundamental studies, but not for building a processor. We really need a more scalable, preferably chemical solution that intrinsically protects the qubit's coherence even in a solid state.
Which brings us to this really quite revolutionary idea I mentioned in the sources. Maybe we shouldn't be encoding the qubit in the spin projection itself, the up versus down. Maybe we encode it in something else entirely.
Yes, this is a very clever approach aimed at tackling the other major source of magnetic noise, which is often even worse than dipolar fields, especially in systems with lots of protons or other nuclear spins around. It's called the Overhauser field.
The Overhauser field.
What's that? It's the effective magnetic field generated at the site of the electron spin, our qubit, by the collective random orientations of all the surrounding nuclear the spins of the nuclei of, say, the hydrogen, carbon, nitrogen atoms in the organic ligands surrounding the metal center.
So the nuclei themselves are magnetic.
Many are, yes, like protons. Hydrogen nuclei have spin 12, and there are usually tons of them in the organic parts of the molecule. Their spins are typically randomly oriented, creating a fluctuating quasi-static background magnetic field.
Like microscopic magnetic static that's always there.
That's a perfect analogy. It's pervasive, unavoidable background noise, and because the electron spin is sensitive to magnetic fields, this Overhauser field rapidly scrambles its phase, leading to very fast 2 decay. It's a huge problem for many spin qubit proposals.
Okay, so how does changing the encoding help? What else can we encode the qubit in?
The really exciting proposal is to encode the qubit not in the total spin projection, like spin up versus spin down, but in the chirality of the spin arrangement within the molecule.
Chirality. Like left-handed versus right-handed molecules, that kind of handedness.
Exactly, that kind of handedness, but applied to the spin texture within, say, a triangular magnetic cluster. You can have spin arrangements that are mirror images of each other, but not superimposable. These are chiral spin states.
Okay. Why would encoding the qubit as left spin-handed versus right spin-handed protect it from the nuclear Overhauser field? That seems non-obvious.
It's subtle but brilliant. The key insight is that these chiral states, the left and right-handed spin configurations, can be constructed such that they have identical local spin projections on each individual magnetic ion within the cluster. Let's call that average projection cis AA for ion I.
So even though the overall pattern is different, left versus right, if you zoom in on any single ion, its average up-down spin component is the same in both the left and right qubit states.
Precisely. And since the decoherence caused by the Overhauser field depends on the coupling between the nuclear spins and these local electron spin projections, S2, if those local projections are identical for both states of your qubit, the left state and the right state, then the Overhauser field simply doesn't differentiate between them.
It can't tell the difference between a 0 and a 1 encoded this way.
Exactly. The qubit becomes effectively invisible or decoupled from the main source of magnetic noise. This geometric encoding strategy could, in principle, completely bypass the Overhauser decoherence mechanism.
And the payoff could be huge.
The theoretical predictions suggest this could push coherence times T2 up dramatically, potentially into the millisecond regime, even in solid-state systems.
Milliseconds. That's a 1,000-fold leap, potentially. That really would be game-changing for molecular quantum computing. Using geometry to store quantum information. Amazing.
It's a fantastic conceptual leap, yes. Very promising direction.
Okay, let's look at another angle on using spins, maybe not just the electron spin, but coupling it to the nuclear spin. There's this fascinating case study using the TBPC2 molecule. Tell us about that.
Right. The bisphosphocyaninato terbium 3-SMM, or TBPC2 for short, It's a remarkable molecule in its own right. It behaves as a very good Ising spin system, meaning its electron spin really only likes to point either fully up or fully down along a specific axis.
Okay.
And it maintains this strong Ising behavior up to incredibly high temperatures, around 600 Kelvin, which is unusual. But the really crucial feature for spintronics is that the central terbium ion, Tb3 plus A, carries a strong nuclear spin. Its value is I equals 32.
So you have the electron spin, which is maybe somewhat volatile, strongly interacting with this underlying nuclear spin, which has multiple states. I32 means 4 states, plus 32 plus 12, negative 12, negative 32.
Exactly. Think of the electron spin as maybe the fast, readable flag or readout mechanism, and the nuclear spin as the much more stable, persistent hard drive for storing information, thanks to its weaker coupling to the environment.
So how did they read the state of the nuclear spin hard drive?
They used an indirect electronic readout method, often involving coupling the TBPC2 molecule to, say, a carbon nanotube, which acts as a very sensitive single electron transistor, or quantum dot. They measure the electrical current through the nanotube, which is sensitive to the magnetic state of the nearby TBPC2 electron spin. Specifically, they can measure the rate at which the electron spin flips back and forth.
And how does that tell them about the nuclear spin?
Because the electron spin and nuclear spin are strongly coupled via the hyperfine interaction. The precise energy levels, and thus the flip rate of the electron spin, depend subtly but measurably on which of the 4 nuclear spin states, the plus 32, plus 12, etc., the nucleus happens to be in at that moment.
So if the nuclear spin is in the plus 32 state, the electron flips at one rate. If the nucleus flips to the negative 12 state, the electron spin starts flipping at a different rate.
Precisely. So by monitoring the electron spin dynamics over time, you can infer the state of the underlying, much more stable nuclear spin. And you can see when or if the nuclear spin itself flips state.
And what did they find when they did this? How stable was that nuclear spin?
The results were quite astounding, really. They could plot something called a transition matrix, basically. A map showing the probability of the nuclear spin being in state J at a later time, given that it was measured to be in state mutually.
Okay.
What they saw was that the diagonal terms of this matrix, which represent the probability that the nuclear spin state remain unchanged between 2 measurements separated by a certain waiting time, were overwhelmingly dominant.
Meaning it mostly stayed in the same state.
Yes, for remarkably long times. Even for waiting times up to around 20 seconds, the probability of finding the nuclear spin in the same state it started in was still very high.
20 seconds. Compared to the microseconds, or even nanoseconds, we were talking about for electron spin coherence. That's practically an eternity.
It's light years away, relatively speaking. It demonstrates the incredible intrinsic stability, the very long lifetime of these nuclear spin states, when they're relatively well isolated within the molecule. It makes the nucleus an extremely robust potential memory element for molecular spintronics. You could potentially write information into the nuclear spin state and have it persist for tens of seconds.
Wow. Okay, so we've covered quantum computing possibilities, ultra-stable memory using nuclear spins. Now let's pivot completely. Let's go to the other end of the thermodynamic spectrum and talk about making things extremely cold. The key concept here is the magnetocaloric effect, MCE. This is the basis for magnetic refrigeration, right?
That's right. MCE is all about the thermal response of a magnetic material when you change the magnetic field applied to it under specific conditions.
Explain the basic cycle. How does changing a field make something cold?
Okay, imagine you have your magnetic material at some starting low temperature. First, you apply a strong magnetic field, typically done adiabatically, meaning no heat is allowed to exchange with the surroundings during the step.
Okay, adiabatic field application.
When you apply the field, you force all the little magnetic moments, the spins in the material, to align with the field. This drastically reduces the disorder or the magnetic entropy of the spin system.
They become more ordered, less randomness.
Exactly. Now, because the process is adiabatic, the total entropy of the material, magnetic entropy plus lattice entropy, must remain constant. Since the magnetic entropy just drops significantly, the material has to compensate. It does this by increasing its lattice entropy, the entropy associated with vibrations of the atoms.
And increasing lattice entropy means?
It gets hotter. The energy removed from the spin system by ordering it gets dumped into the lattice as heat. So, step 1, applying the field adiabatically actually heats the material up.
Okay, doesn't sound like cooling yet. What's next?
Next, while the field is still high, you allow this extra heat to flow out into a heat sink, bringing the material back down to the starting temperature, or maybe even lower. Then comes the cooling step. You remove the magnetic field, again adiabatically.
Adiabatic field removal.
Now the spins are free to randomize again. They rapidly absorb thermal energy from the lattice to regain their high magnetic entropy state, their disordered state. Since they're sucking heat out of the lattice adiabatically, the lattice temperature plummets.
There's the cooling.
That's the cooling stroke. The material gets significantly colder than its starting temperature. This whole principle of magnetic refrigeration is particularly effective at cryogenic temperatures, say below 20 Kelvin, where conventional gas cycle refrigerators become less efficient.
Okay, so if we want to make this practical, especially using molecules, we need materials that really maximize this effect. What are the ideal properties? What makes a good molecular magnetic refrigerant?
Well, thermodynamically, the goal is to maximize two key figures of merit. First is the adiabatic temperature change, delta tad basically. How much colder does it get in that final step? Second is the magnetic entropy change, delta sullum. How much entropy can the spin store and release?
And what chemical or structural features give you big values for those?
Our sources lay out about 4 essential criteria for designing the ideal molecular cooler. First, you need a large spin ground state for the magnetic centers. A bigger spin means more possible orientations, hence more magnetic entropy available to be manipulated.
Makes sense. More states to randomize into. What else?
Second, you need negligible magnetic anisotropy. Remember the anisotropy barrier in SMMs? That splits the energy levels even at zero field. For cooling, you want the opposite. You want all the spin states to be nearly degenerate, same energy, at zero field, so that removing the field makes all the entropy available right down to the lowest temperatures. Anisotropy would limit that.
Okay, large spin, low anisotropy.
Yeah.
Third,
you ideally want weak ferromagnetic exchange interactions between the spins. Weak interactions mean they don't order spontaneously until very low temperatures, preserving the paramagnetic state needed for MCE. Ferromagnetic spins wanting to align is slightly better than antiferromagnetic wanting to oppose because it can enhance the response to the applied field a bit.
Right. And the fourth criterion sounded more structural, related to efficiency.
Yes, the fourth one is absolutely critical for practical applications, especially miniaturization. You need a large magnetic density. This is basically the ratio of the mass of the magnetic metal ions to the total mass of the molecule or material, including all the non-magnetic organic ligands, counterions, solvent, etc.
Why is that so important?
Because the magnetic ions are doing the cooling work, but they have to cool down the entire material, including all the non-magnetic deadweight. So you want the highest possible fraction of the mass to be the active magnetic component. Maximize the cooling power per unit volume or per unit mass.
Okay, large spin, low anisotropy, weak ferromagnetic coupling, and high magnetic density. That's the wish list. And this leads us almost inevitably to one particular element, gadolinium.
Gadolinium, specifically the GD3+ ion, GDO, is almost perfectly tailor-made for low-temperature magnetic cooling. It really embodies those criteria beautifully.
How so?
Well, first, it has a very large spin, S equals 72. That's huge, giving it a large magnetic entropy, RLN2S+1 equals RLN8. Second, and crucially, gadolinium is a lanthanide. Its magnetic 4f electrons are buried deep inside the atom, shielded by outer electron shells.
And that shielding means?
It means they interact very weakly with the surrounding chemical environment, the ligands. This results in negligible magnetic anisotropy fulfilling criterion 2 perfectly, and also very weak exchange interactions between neighboring GDO ions fulfilling criterion 3. It's the textbook example of a large isotropic weakly interacting spin system.
Okay, so gadolinium itself is the ideal magnetic atom. The challenge then becomes building a chemical structure around it that satisfies the fourth criterion, that high magnetic density.
Exactly. You need to pack these ideal G ions together as closely as possible, using the lightest possible non-magnetic glue to hold them together. You want to minimize that dead weight.
And the sources highlight a specific type of structure that achieves this.
Correct. They point to highly compact structures, and a really fantastic example is a three-dimensional metal organic framework, or MOF, with the formula GD. This is built from G ions linked together by formate ligands.
Formate. That's HCOO. That's a very small, light ligand, isn't it?
Incredibly light, just hydrogen, carbon, and 2 oxygens. Using these tiny formate linkers is key. It allows the GO ions to be packed relatively closely in a 3D network while minimizing the mass of the non-magnetic framework.
So this structure compact lattice, super light ligands, gives it a remarkably high magnetic density, hitting that fourth criterion hard.
Precisely. It maximizes the amount of cooling power, the G2 spins, per unit volume or mass.
So let's talk performance. How does this gadolinium formate MOF actually stack up when you measure its cooling capacity? Say, the volumetric MCE, the cooling power per cubic centimeter. How does it compare to materials already used in industry?
It stacks up exceptionally well, especially for its class. That's why it represents a significant step forward for molecule-based refrigerants. Its volumetric MCE maxima were reported in the range of 120 to 189 millijoules per cubic centimeter per Kelvin, MJCMU, for magnetic field changes of 1 to 3 Tesla.
Okay. Are those numbers good?
Yes, those are very competitive numbers. To give you some context, achieving high cooling power per unit volume is crucial if you want to make small integrated cooling devices. These performance figures compare very favorably with some conventional inorganic refrigerants used at low temperatures, like the benchmark material gallium garnet or GGG, and they are definitely superior to most other molecule-based refrigerants that have been developed before.
That volumetric performance really is key, isn't it? It suggests that the future here isn't just about making bulk cooling materials, but about integrating them, maybe making tiny refrigerators.
Exactly. That's the direction things are heading. The ultimate goal is often micro-refrigeration. The idea is to be able to graft or deposit thin layers of these high-performance molecular magnetic coolers directly onto substrates, maybe onto the chips themselves.
Substrates with high thermal conductivity to efficiently transfer the cooling.
Right. You could envision creating dedicated, highly efficient cooling units integrated directly onto sensitive electronic components that need stable cryogenic environments. Things like superconducting quantum bits or highly sensitive detectors used in astronomy or fundamental physics. This really moves MCE from being just a bulk cooling technique toward being an active component in complex miniaturized quantum hardware.
Okay, we spent most of our time talking about these zero-dimensional magnetic objects, the single molecule magnets. Now let's briefly broaden the scope and look at what happens when you go to one dimension. Single chain magnets, or SCMs. How does the fundamental magnetic physics change when you arrange these magnetic ions in a line instead of a cluster?
It changes quite dramatically, actually. The underlying mechanism responsible for the slow relaxation of magnetization, which is the defining characteristic of both SMMs and SEMs, is completely different.
So SEMs also show slow magnetic relaxation, like SMMs. They can act like magnets below a certain temperature.
Yes, they do exhibit slow relaxation. But as I said, it's not governed by quantum tunneling of magnetization, QTM, between states of the entire chain, like it is for the cluster and SMMs. Instead, the slow relaxation in these one-dimensional SEMs is dictated by the physics of thermally excited domain walls moving along the chain.
Domain walls? What exactly is a domain wall in a 1D chain?
Imagine you have a long chain where all the spins are initially pointing up, fully magnetized. A domain wall is essentially the boundary or the transition region between a segment of the chain where spins point up and an adjacent segment where the spins point down.
So it's like a flip propagating along the chain.
Sort of. You need thermal energy first to create or nucleate such a domain wall pair, one up to down wall and one down to up wall. Once created, these walls can then propagate along the chain, effectively reversing the magnetization of segments as they move.
And the speed of relaxation depends on how easily these walls form and move.
Exactly. The overall magnetic relaxation rate is determined by the energy barrier to nucleate these domain walls and the energy barrier for them to hop or propagate along the chain. It's a thermally activated process.
So their behavior sounds much more analogous to how we think about magnetization reversal in, say, long, thin magnetic nanowires or elongated nanoparticles.
Precisely. SEMs serve as really excellent chemically precise model systems for understanding the finite temperature magnetic dynamics of these larger, elongated magnetic nanostructures. Their behavior is often analyzed using theoretical frameworks like the Glauber model, which specifically describes single spin flip dynamics and relaxation driven by thermal activation and domain wall motion in 1D systems.
Okay, so that's a crucial distinction. QTM dominates the slow relaxation in 0D SMMs, while thermally activated domain wall dynamics dominate in 1D SEMs.
Got it.
Now, let's take the next step towards actual devices, putting these molecules onto surfaces. The sources mentioned using metal fillet cyanines, MPCs, for this.
Yes, this is where molecular electronics really starts to merge with molecular spintronics. Metal phyllocyanines are great candidates for this. They are these relatively large, flat, robust organic molecules that have a central metal ion holding the spin. Their flatness makes them ideal for depositing nicely onto surfaces.
So you can study individual molecules on a substrate.
Right. But the key challenge in the fascinating physics arises the moment that molecule touches the surface, especially if it's a conducting metal surface. Its intrinsic magnetic properties can be fundamentally altered or even completely changed by the interaction with the substrate's conduction electrons.
And this interaction can manifest in basically two major and often quite opposite ways. You can get the Kondo effect, where the magnetic moment can just get completely quenched.
Exactly. Those are two common outcomes. Let's start with the Kondo effect.
Okay.
The Kondo effect is this really neat quantum phenomenon that happens when you have a localized magnetic moment, like the spin on the metal ion in the MPC, interacting with a sea of delocalized conduction electrons like those in a gold or silver substrate.
What does the interaction do?
What happens is that the conduction electrons in the substrate effectively gather around and screen the molecule's localized spin. They form this collective many-body state, a spin singlet between the molecular spin and the conduction electrons.
So the environment essentially hides or cancels out the molecule's magnetism at low temperatures.
That's a good way to think about it. The magnetic moment is still there, but it's locked into this non-magnetic entanglement with the substrate electrons. The experimental signature is usually a sharp resonance appearing right at the Fermi level in the electronic density of states, which can be measured using techniques like standing tunneling spectroscopy, STS.
And this was seen for iron phyllocyanine on gold.
Yes, single FePaPac molecules deposited on a gold-ellipse surface clearly showed this Kondo resonance. They could even measure the characteristic energy scale of this interaction, the Kondo temperature TK, which was found to be around 2.6 Kelvin for that specific system. It confirms that strong quantum coupling between the molecular spin and the substrate.
Okay, so that's one outcome. The spin is still there but gets screened. What about the other outcome? Quenching, where the magnetic moment just disappears entirely.
Right, that's the quenching mechanism. And this was observed, for example, when cobalt phyllocyanine, COPAC molecules, were deposited onto conducting surfaces like gold-11 or silver-100. In this case, experiments showed that the magnetic moment of the COPAC molecule was totally quenched. It effectively became non-magnetic, with a resulting spin state of S = 0.
Why does that happen? Why would it just disappear?
It's usually due to charge transfer and strong hybridization between the molecule's orbitals and the electronic bands of the metal substrate. The energy levels line up in such a way that an electron might transfer from the metal into one of the frontier orbitals of the Copic molecule, or vice versa.
So adding or removing an electron changes the molecule's electron configuration.
Exactly. And it changes it in such a way that the spins now pair up, leading to an overall non-magnetic SEL0 ground state for the molecule on the surface system.
So in simple terms, the close contact with the conducting substrate forces the molecule into a different electronic state, one that happens to be non-magnetic.
Yes. And that single result, the fact that the inherent magnetic moment of Copic can be completely destroyed just by placing it on a common metal surface, really underscores the profound and immediate influence of the substrate environment. It highlights the central challenge, but also the opportunity in molecular spintronics. You can spend years chemically engineering the perfect isolated spin molecule, but the moment you try to wire it up, connect it electronically, its fundamental magnetic identity might be completely redefined by these surface interactions like hybridization and charge transfer. Controlling that interface is key. #outro.
Wow. What a journey through this field. It really feels like we've gone from the incredibly tiny, the quantum mechanical mystery of a single molecule tunneling.
Yeah, that QTM and SMMs where applying a field just right opens these discrete quantum door.
Allowing predictable tunneling across that massive energy barrier. And then we scaled all the way up to these surprising, almost explosive macroscopic effects like magnetic deflagration.
Right, where those tiny quantum flips can trigger these propagating spin reversal fronts driven by heat, or even, potentially, by pure quantum self-organization in the cold deflagration scenario.
And we saw how all this fundamental understanding is directly feeding into potentially revolutionary applications in three really distinct areas.
Absolutely. First, quantum computing. SMMs as potential qubits, and especially that clever idea of encoding information in spin chirality to maybe achieve millisecond coherence times by dodging the Overhauser noise, that's huge.
Definitely. Second, molecular spintronics, using molecules for memory or logic. The TBPC2 example was stunning, leveraging the stability of the nuclear spin to get memory lifetimes possibly reaching tens of seconds.
Incredible persistence for a molecular system. And third, we covered molecular magnetic refrigeration, using the GDO paradigm.
Right. Chemically engineering these compact MOFs with really light ligands to maximize that magnetic density.
Achieving volumetric cooling performance that's genuinely competitive with traditional materials, especially at cryogenic temperatures, which really opens the door for things like on-chip microrefrigeration.
It feels like the common thread running through everything we discussed is this theme of control, doesn't it? Pushing the boundaries of controlling matter and quantum mechanics at the molecular level.
It really is. The ultimate frontier here isn't just synthesizing new molecules. It's about precisely engineering the molecular environment, the interactions, the boundary conditions, and using that to control the resulting quantum mechanical behavior.
And you mentioned these systems allow us to probe some really fundamental physics, too.
Yeah. This field gives us unique playgrounds to investigate things like non-equilibrium spin dynamics. We talked about domain wall nucleation and propagation in chains. Studying those processes in exquisite detail, especially as we push systems towards absolute zero temperature and approach a quantum critical point where phase transitions are governed purely by quantum fluctuations.
That sounds like the ultimate laboratory for understanding quantum phase transitions.
It is. And it's not just fundamental curiosity. Those kinds of studies, understanding how to control the dynamics of a quantum system as it evolves, especially near critical points, they're directly relevant to implementing advanced quantum computing protocols. Specifically, things like adiabatic quantum computation, or AQC.
Adiabatic QC.
Hey.
That's where you slowly morph the system from an easy state to a complex one that encodes the answer.
Exactly. AQC relies on being able to gently steer a quantum system along its ground state path, often traversing quantum phase transitions slowly and coherently to solve hard problems. If we can gain the level of control over the magnetic evolution of these molecular systems that we've been hinting at today, being able to guide them smoothly across these transitions, that could open up entirely new and potentially powerful avenues for quantum computation and simulation, leveraging the intrinsic quantum laws that govern these truly exotic molecular magnets.
Controlling quantum phase transitions at the molecular level for computation, that truly feels like the deepest dive into the future of magnetic materials.